Hello and welcome to Multivariable Physics, Part 3. And now we're actually going to be talking about physics for after 10, 15 episodes. So, hopefully I got some of the math that we're going to be using out of the way, so some of this makes sense. This is going to be a very early episode where I'm not going to talk about too much. There's not going to be a lot of interesting stuff going on, at least for now, but we're going to be talking about these physics. So the first thing we're going to be doing is just thinking about how we can apply everything we've learned to physics and how is this relevant in physics. So the first thing is obviously scalar functions and vector functions have their place in physics. Obviously vectors, so if we think about space, we think of things, we like to think of things in 3D space. Well, we have something, let's say we have a particle moving in 3D space, right? We have this R here. So this path, we can describe this path as like a vector from the origin, right? We have some R, and then this R can vary over time, right? And so this R, this is just a vector function. This is a vector value function. And this is going to parameterize that path down that curve, right? And then I think I already mentioned this before. You can take, our velocity is equal to r dot, and then acceleration is equal to r double dot, right? So that's one thing, but how these things connect to vectors is, or physics is also, we have forces. Forces act on things. So you have the force on a particle. Well, that's just m r double dot, right? Newton's which law is this? This is Newton's first law, I'm pretty sure. Maybe I'm wrong. I should know this because I'm a physics major. But yeah, we have for Newton's law, right? F equals ma, right? That's all that is saying, right? And this is a vector value function where r is just, this is the vector function that parameterizes the acceleration over time, right? That's all that is. But then we also have, change of variables. So we have different coordinate systems in physics. So we have, Cartesian, x, y. And then we also have radial, r, and then, theta, right? So we have this transformation, we have this transformation where if we have xy, r is equal to x squared plus y squared, and theta is equal to tan x over y, or arctan, sine over cosine, which is actually y over x, right? So we have this kind of change of variable functions, or alternatively we have x equals r cosine theta, y equals r sine of theta, right? That sound good? So this is remember what I talked about, how we have, this is change of variable because the dimensions are the same. A vector function from the same dimension to the same dimension, right? This is a vector function, it's a space curve, vector function from a lower dimension to a higher dimension, right? N is less than m. But then we have scalar functions. So we can take scalar functions. So we have the potential energy at a point. I'm going to draw this as like a contour plot. So here's the Earth. And then the potential energy, here we have one line, another line. And, the closer we get to Earth, the smaller and smaller our potential energy becomes, right? And then we can do, well, what happens if you take the gradient? So this is obviously Earth, so I'm going to draw some happy people on it. It's on fire. But what happens if you take the gradient of U? Right? Or in this case, the negative gradient of U. Well, that's going to give us, so we get Earth. And then we're going to end up getting this. A vector field. This is the field of gravity, essentially. So the gravitational field around Earth. Right? And I'm slow at drawing, but yeah, right? So we found that if we take the gradient of this scalar potential field, we get a vector field, because remember that the gradient applied to a scalar function is a vector value function, right? So we have this relationship here, f of g is equal to the gradient, or the negative gradient, of u of g, right? For some point in space. And yeah, and so anytime we actually have this case, this is actually called, so anytime we can derive a force from some potential energy, it is called conservative. This is called a conservative vector field. And that's, I think, all the time I have for this bit. The next bit I'm going to actually start talking about using, doing things with these things. So I'm going to talk about coordinate systems, or inertial frames of reference in coordinate systems, what I'm going to talk about next. And then we'll talk about, translating between coordinates and stuff like that.